Hi, class. For homework, I asked you, hey Teresa, hi Raksha. For homework, I asked you to have a look at 684. And on page 684, the practice exercise says, what is the concentration of a solution of potassium hydroxide for which the pH is 11.89? And then B, calcium hydroxide for which the pH is 11.68. Starts off with KOH concentration not known, but the pH is equal to 11.89. So if you take the reciprocal, or the inverse of the log, what you get is the OH minus concentration. Sorry, no you don't, because I need to find the H. Yeah, the H plus concentration is going to be 10 to the negative 11.89, which gives you 1.28824955 times 10 to the negative 12 molar. But what they're asking you for is the OH minus concentration. Since in aqueous solution, when you multiply the concentration of protons by the concentration of hydroxide, you get 10 to the negative 14. Then you can find the OH minus concentration by dividing it into the 10 to the negative 14. What you get is an OH concentration equal to 7.76. 247 times 10 to the negative 3. So because KOH is a strong base, you know it dissociated completely, and therefore you're going to get the same concentration of base as you had of OH minus in the solution. So the KOH concentration equals the OH concentration, which equals, after sig figs, 7.8 times 10 to the negative 3 molar. That was A. I'll give you a moment to write that down. I'll do part B. In part B of the same question, what they ask is calcium hydroxide concentration for a pH of 11.68. So they're asking for calcium hydroxide concentration, and they know that pH equals 11.68. Since we could do it a slightly different way than the way you did A, but you still get an answer. Since pH plus POH equals 14, we can just switch to POH. So therefore the POH is going to be equal to 14 minus 11.68, which gives you 2.32. Therefore the OH concentration is going to be 10 to the negative 2.32, which gives you 4.7863 times 10 to the negative 3. Now, calcium hydroxide concentration will be half of that, because one equivalent of calcium hydroxide yields 2 equivalents of hydroxide. So take half the concentration of that. Times 1 calcium hydroxide for every 2 OH minuses. Oh, I'm going to write it there. So what you get is 2.393 15046 times 10 to the negative 3 molar. And so the calcium hydroxide concentration will be equal to 2.4 times 10 to the negative 3. You'll see in the notes that metal oxides are very effective at forming alkaline solutions. So the name alkali metals and alkaline earth metals comes from that property. If you take something like sodium, you put it in water, metallic sodium that is, not an ionic form of sodium, but if you take an oxide of sodium, and how do oxides of sodium form? If you took pure sodium metal, it would oxidize as soon as you expose it to the air. It would react. If you cut a piece of sodium, it tarnishes instantly because of the reaction with the oxygen and the water in the air. If you then put that in water, you would get a reaction where, first of all, it would dissociate, but the oxide ion would not persist in that form. It would quickly combine with water, or react with the water to form 2 hydroxides. So it'll actually pull a proton off the water, and then you'll end up with 2 hydroxides. So the water losing a proton becomes OH minus, and the oxide gaining a proton becomes hydroxide. So out of this, you get 2 hydroxides. So you can see why oxides of alkali metals and alkaline earth metals both will produce alkaline solutions that have pH greater than 7. And hydrides and nitrite also form hydroxide in aqueous solution. On page 684, give it some thought. It shows that the methane with a negative charge, the CH3 minus ion, is the conjugate base of methane. And methane shows no evidence of being an acid in water. What happens when the CH3 minus ion is added to water? Well, it just pulls a proton off water and generates methane. What you get is this: CH3 minus plus H2O will generate methane, and you get hydroxide. It'll basify the water. But methane, it actually won't go the other way. It's a one-way reaction. The equilibrium going that way is negligible. Because weak acids only partially ionize, they can be portrayed as HA rather than drawing the whole molecules. And weak acids can be portrayed this way. You say HA, where H is the ionizable proton, and when it ionizes, you get H plus, and the rest of the molecule, which you call A minus. Like for example, if you have acetic acid, the proton will come off the acetic acid, and then the acetate anion would be represented by just A with a minus on it. It just makes it easier to do calculations where you have to have a lot of variables being bounced around. Just makes it more efficient. Also, when you write an equilibrium for acids, you get Ka, right? So K, the acid dissociates into a proton and its conjugate base. So you always write products over reactants whenever you do equilibria. It's always product concentrations over reactant concentrations, whatever they are. There might be more than one. So in the case of a weak acid, you're going to get a proton dissociating its anion and then the undissociated acid is the reactant. So products over reactants. And you could also use an ice table to calculate the concentrations of acid in a weak acid solution. ICE stands for initial, change, and equilibrium. So you're just keeping track of all the concentrations, because sometimes setting up the equation can be fairly complicated and it's hard to keep it all straight in your head, so it's better to just write it down. As an example, I'll do practice on page 687. You see what it looks like. So niacin, I'll draw it all out. Niacin looks like this. It's an organic acid. There's the ionizable proton. When it dissociates, you get niacinate. And the proton. You can set up an ice table. Initial, concentrate, change, and equilibrium. So initially, in the problem, you have 0.020 molar concentration, and you have 0 of the other things. Before the reaction happens, you have 0 and 0 of the products. It says after the reaction, that the pH is 3.26. Well, if the pH is 3.26, you're going to easily be able to calculate the H plus concentration. So let's do that at the bottom here. If pH is equal to 3.26, then the H plus concentration is equal to 10 to the negative 3.26. You do that, you access this calculation by doing inverse log. You'll see it on your calculator. And what you get is 5.495 4087 4 times 10 to the negative 4 molar. So that's your concentration of H plus. And you can write that here because that's at equilibrium. So 5.495, etc. I'm not going to write the whole thing. And also for this one, 5, because if you have that much H plus, you also have the same with the niacinate. Where's the H plus coming from? It's coming from here. So when that dissociates, it produces the same amount of niacinate. So both these numbers are the same. Okay, so it's plus that number, 5.495 times 10 to the negative 4, plus 5.4. So you don't always need the full table. Just use the table as a tool. If you don't need the tool, don't use it. But it's good to keep track of what you're doing, showing your work. Here, you're going to have to subtract that amount, because whatever amount of H plus is produced, that's the amount that's being subtracted from the original. So 5.495 times 10 to the negative 4. So what that gives you is 1.94. When we subtract this from this, that's how much is left. 1.94504591 times 10 to the negative 2. So now we have to establish the percent ionization. I'll write that, how we do that here. Percent ionization is equal to the H plus concentration over the initial niacin concentration times 100. Turn it into a percent. You enter all the numbers, it's this number, 5.495 times 10 to the negative 4 over the original niacin concentration, which is 0.20 times 100. What you get after sig figs is 2.7% ionization. So clearly, niacin is a weak acid. It only gives you 2%, 2.7% ionization. In part B of the same problem, it says, what is the acid dissociation constant for Ka, or Ka for niacin? So Ka will be equal to the niacinate concentration times the H plus concentration times the concentration of the original niacin. And what you get is 5.495 times 10 to the negative 4 squared over 0.020. No, sorry, not 0.0, it's the concentration at equilibrium. So it's 1.945, etc., times 10 to the minus 2. What you get is 1.5526, 3776 times 10 to the minus 5. And normally you report these to only one decimal place, so 1.5 times 10 to the negative 5 is your Ka value for niacin. So what can you, there's more than one way to do these calculations, and I'm going to show you one big long calculation to show you how it's done. The first way is to just do an approximation, and typically the first way will work. 90% of the time it works and gives you the answer. If you want to be sure that you got the exact answer, you can use the quadratic formula, because these things always generate trinomials. And then there's yet a third way called iteration, where you can converge to the answer by plugging into first doing the approximation type calculation. Now once you get a preliminary answer, you plug the preliminary answer back into the original equation, and you keep plugging it into the same equation until it converges to the correct answer, and it'll give you exactly the same answer as the quadratic formula. This is probably not the best place to do it because that board is minuscule, but I did post it already on my chapter 16 notes. If you go to page 8 and 9, you can see that calculation. You have the regular, the approximation, quadratic formula, and iteration, the three different ways. All three of them will give you the same exact answer. And you could do it for the mathematical fun of it. But really, if you want to play it safe, you just use the quadratic formula every time you get the correct answer, the exact answer. So let's go to page 688, where it asks you to give it some thought. Mao? You paying attention? He's just sitting there on his haunches. Why can we generally assume that the equilibrium concentration of a weak acid equals its initial concentration? Let's give it some thought on page 688. I write, we can normally assume that the equilibrium concentration of a weak acid is the same as the original concentration of the acid, because weak acids are only slightly ionized. The amount of dissociation does not put a big dent in the original amount. You know, if only 2.7% of the thing ionizes, if you assume that it's still completely unionized, you haven't added a huge error to your calculation. And you'll see when we do we're going to do a sample right now. So page 689 then. This is practice exercise. On my notes, I do a sample calculation where I assume 0.1 molar concentration of niacin, and then I noticed later on that the question asks 0.01 molar. So be careful you don't get confused like I did. But I show you the two different ways of doing the calculation. Just noticed I made a little mistake in here somewhere. I have to check my results. Anyway, I'm going to practice example on page 689. So it says the Ka for niacin is 1.5 times 10 to the minus 5. What is the pH of a 0.01 molar solution? So you have a 0.01 molar niacin, and they want to know what the pH is. So let's call niacin HNI, just to make it easier to do write all the calculations out. So you got the undissociated niacin with the ionizable proton there, and then it dissociates into niacinate and a proton. Now let's do an ice table. Initially it's at 0.01. A certain amount X dissociates, so at equilibrium it'll be 0.01 minus X. Initially there's 0 niacinate, but a certain amount X appears equal to the amount that disappears here, and at equilibrium you'll have X. The H plus, same thing. At equilibrium you have X amount present. So these are the quantities you're interested in at equilibrium. We know that Ka is equal to 1.5 times 10 to the negative 5, and that this gives us the concentration of niacinate times the concentration of H plus over the concentration of the original undissociated niacinate, and it's going to be represented in this case by X squared over 0.01 minus X. So that's going to create a quadratic equation. But let's do it the simplification way, okay? We know that this minus X is going to be a tiny amount. Well, I'll show you both ways. I'll show you first the approximation way. So the first way is the approximation now. Let's pretend, using the approximation calculation, that this is really small. So we could just ignore it. So if we just ignore that minus X part, this turns into X squared over 0.01. So then it simplifies our calculation down to 1.5 times 10 to the minus 5 is equal to X squared over 0.01. So that gives us X equals 1.5 exponent negative 5 times 0.01 gives negative 7, right? And that equals to X squared. So if I take the square root of that, I'll get what? Oh no, don't. Okay. So what we get is this. We get that X equals, we get that X equals 3.8729 times 10 to the negative 4. If you take the log of that, it's going to give you the pH, because that's equal to the H plus concentration. I just told you that X equals the H plus concentration. So take the pH, negative log 10 of that, you get a pH of 3.41. Now let's redo the calculation using the quadratic formula and see what it yields. There's enough room. All right, so if you distribute this, you do a cross multiplication, you get X squared equals 1.5 times 10 to the negative 5 times 0.01 minus X. So that gives you X squared is equal to 1.5 times 10 to the negative 7 minus 1.5 times 10 to the negative 5X. Transpose everything to one side. X squared plus 1.5 times 10 to the negative 5X minus 1.5 times 10 to the negative 7 equals 0. Plug that into the quadratic formula. If you don't have a calculator, X equals to b squared plus or minus the square root of b squared minus 4ac all over 2a. But we live in the 21st century and we have calculators that will do that for you. So, mode, okay, here's my calculator, mode, press equation, then you get a pop-up menu, it says 2 variable linear equation, 3 variable linear equation, quadratic, ooh, quadratic, 2. Now you get these three numbers appearing, A, B, C, 0, 0, 0, and you have to enter in each one of the values. So the first value is 1, so enter 1, and then enter. Then it goes to, the flashing cursor goes to B, and then the value of B is 1.5 exponent negative 5. Enter. You see, now the flashing cursor goes to the third position, and you get negative 1.5 exponent negative 7. Enter. And it gives you two values. Why are there all these horrible reflections? So you get a positive value and a negative value. Obviously, you're going to discard the negative value because you can't use it. You can't get a negative concentration. So the two numbers that you get, two possible solutions to your quadratic formula, are 3.798, 70946 times 10 to the negative 4, or negative 3.94870946 times 10 to the negative 4. Okay, I have to exercise judgment. This is the correct one. That doesn't work in our universe. Maybe it works somewhere else. It doesn't work here. So you pick one, and then if you take, that's your H plus concentration. Okay, so you can find your pH now. pH equals negative log of the H plus concentration. Let's plug it in and see what we get. It's going to be pretty darn close. So log of 3 point, no, I got to get back in normal mode. Okay, so log of 3.79870946 exponent negative 4 gives you pH of 3.42. All right, so it gives you a tiny difference from the approximation. You get 3.41 with the approximation. You get 3.42. This is more exact. But would you get marked wrong in the test? Of course not, because both are good. However, what I might do is say, give me the answer using the quadratic formula, or give me the answer using the approximation, or even better, give me the answer both ways. So don't get lazy. Then on 691, this is practice exercise. We found that the percent ionization of niacin, Ka equals 1.5 times 10 to the negative 5, in a 0.02 molar solution is 2.7%. Calculate the percentage of niacin molecules ionized in a solution that is 0.01 molar, or B 1.0 times 10 to the minus 3 molar. So you'll notice that with weak acids, the more dilute the acid is, the higher the percentage of ionization. We're running out of time. You know what? This is half an hour already. Let's give you that one for homework. Page 691. Yeah. So, homework, practice example, page 691. Try not to look at my solutions when you do it. If you can do it, I don't know, if you're stuck, obviously go to my solutions. Same as always. All right? And we'll see you tomorrow. Bye-bye.